Okay, hi everyone. So welcome to lecture number 8 of counting. So we are doing GATE Data Science and Artificial Intelligence complete course, and we are discussing counting. Right now we have seen factorial, the motivation behind factorial, permutations, which means arrangements, and then combination, which means selection, then combination with repetition and permutation with repetition, and we have solved a few problems on that. Now we are going to a new topic which is called the binomial and the multinomial theorem. Okay, firstly, these two are mathematical theorems, and they have their own motivation, and they are completely into maths. Okay, why are we discussing them in counting? We will see it. What do multinomial and binomial theorem have to do with counting? We will see that. Okay, so yeah, let's start. Firstly, what is binomial theorem and why are we discussing it? So, what is binomial? A polynomial with two unknowns. So basically, let's say x plus y to the power 2. This is a binomial. Okay, we have two variables and there is some power. Okay, we are raising it to some power. So we already know that what is x plus y whole square? It is x square plus 2xy plus y square. This is the binomial theorem for power 2. What is the binomial theorem for power 3? What is x plus y whole cube? So basically you are multiplying x plus y with x plus y, and basically you are expanding this bracket. So what are you essentially doing? So let's say there are three containers, right? There are three containers. All three of the containers have one x and one y. Right. So in how many ways can you take x and y? So that is what binomial theorem is. That is why we are discussing it in counting, right? You are seeing that mapping, right? You have three containers, all of them have x and y. In how many ways can you have three x's? So you will have one, so in this expansion you will have one term for x cube. So either you can take three x's, or you can take two x's and one y, or you can take one x and two y's, or you can take all three y's. So in this expansion, you will have all these three terms. So in how many ways can I take three x's? So you take one x from here, and basically x from all three of them. So there is only one way. Plus, so in how many ways can you take two x's and one y? You can take x from here, and y from here. Or you can take x from here, y from here, and x from here. Or you can take y from here, x from here, and x from here. So there are three ways in which you can take two x's and one y. So there will be 3x square y. When you expand it, you will get this only, right? Similarly, there are three ways in which you can take 1x and 2y's. Like similarly, you can take x, y, y, x, y, x, x, y, 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 x, y, and y, y, x. So there are three ways in which you can take 2 y's and 1 x. And there is only one way in which you can take all 3 y's. You just take y from everywhere, okay? So when you expand it, you will get 8 different terms. One of which will be x cube, one of which will be y cube, 3 of which will be x square y, and 3 of which will be xy square. So this is what binomial theorem is for power 3, right? And this is how we get it connected to counting. You consider n containers. In how many ways can I pick 2 x's and 1 y, right? So this is what binomial theorem is. So the generic expression for binomial theorem, if you create it this way. So let's try to derive it on our own. Okay, I will try to derive a generic expression for x plus y to the power n. So this is binomial theorem for power n. Okay. So here what we will have? Here we are multiplying x plus y with x plus y, then again x plus y, and so on. Basically, we are multiplying x plus y bracket n times. 1, 2, up to n times. Right? So basically, when we multiply, what will we get? So if we take x from everything, x into x into x, we can get x to the power n. So we will get different terms. Okay? But you will see a pattern. You will see one term will be x to the power n. You will have few terms of type this, x to the power n minus 1 and y. you will have a few terms of this type, x to the power n minus 2 y square. Similarly, and you will have one term like y to the power n. Basically, you will have many such terms, but the sum of coefficients of x and y will always be n. Here you have n x's and 0 y's. You can write it like this also. N x's and 0 y's. Or you can have n minus 1 x's and 1 y. Basically, again the same thing. You have n containers. Right? You have n containers. All of them contain 1 x and 1 y. You can either take an x or a y from every one of them. So basically at the end you will have some number of x's, some number of y's, but the total number of x and y will be always n. So the sum of coefficient, the sum of the powers of x and y, sorry, not coefficients, sum of the power of x and y will always be n. Right? Now, what will be the coefficient? So in how many ways can I pick n x's and 0 y's? So basically, from all the n containers, you are picking x only. There is only one way. There is only one way you can do this. In how many ways can I select n minus 1 x's and 1 y? So basically what you are doing is, from n minus 1 containers you are choosing x, and from only one container you are choosing y. So basically you choose that one container from which you are taking y. See, the simpler problem to think about it is, in how many ways can I choose one container, and from that one container I will take y, and from all other containers I will take x's. So there are nc1 ways. There are nc1 ways in which I can choose that container from which I am taking y. Similarly here, in how many ways can I have n minus 2 x's and 2 y's? This can be said as, in how many ways can I pick two containers and I will take y from them, and from the remaining n minus 2 I will take x. So basically there are nc2 ways in which you can choose those two containers from which you are taking y, and from the remaining containers you will pick an x. So this is the coefficient of x to the power n minus 2 and y to the power 2. Similarly, at the end, for y to the power n, you will have ncn, or 1 again. So this will be the expansion. So here n1 can also be written as nc0, because we are taking 0, because actually you are taking no containers with y. So you are taking 0 containers. You are picking 0 containers from which you will take y. So this is the expansion of x plus y to the power n. Right? So you can also like write a compact notation for it, but yeah, like this is the generic equation for x plus y to the power n. So like this is the compact notation. How do you write it? So x plus y to the power n will be summation from k equal to 0 to n choose k. So n choose k is the coefficient. So k, here k is equal to 0. K is the, let's say k is the number of y's. K is the number of y's that you are taking. So you are taking n minus k x's. So pick any k out of n boxes. From those you will take a y, and from remaining you will take an x. So the coefficient will become n choose k, and the product will become x to the power. So basically you are picking k y's and n minus k x's. Sum of the power will always be n, and the coefficient will be n choose k. So and the sum goes from k equal to 0 to n. So this is what this expression is, right? And similarly, the same way you can also choose x also, right? Why only choose y? You can choose x also. Let's say first I am choosing 0 x's and all y's. Then I am choosing 1x and 0 y, 1x and n minus 1 y. And at the end I will choose n x's and 0 y's. You can also choose x's instead of y's, and the coefficient will remain same. Out of n, choose 0 boxes from which you will take x, and from remaining you will choose y. So like yeah, and you can also derive this formula from this formula. You can just write NCR as NCn minus r. So this coefficient will become NCn, and this coefficient will become NCn minus 1, and at the end this coefficient will become NC0. Okay, you can do k selection equal to k rejection. So also this formula becomes this formula. So the power of x can be k and y can be n minus k. Here you are selecting y, here you are selecting x. Doesn't matter, right? So it is symmetric in some sense. It is symmetric in some sense. So what happens? Let's say I calculate x plus y to the power 5. Here I will have 6 different terms. X to the power 5, x to the power 4y, x cube y square, x square y cube, x y to the power 4 and y to the power 5. I will have 6 different terms and the coefficient of x to the power 5 will be what? Since we are choosing 0 y's, so this coefficient will be 5c0. This coefficient will be 5c1 because I have to choose one y. This coefficient will be 5c2. This coefficient will be 5c3. And this coefficient will be 5c4. And this coefficient will be 5c5. Right? If you just write the values also, 5c0 is 1. So this will become x to the power 5. 5c1 is 5. So it will become 5x to the power 4y. 5c2 is what? 5 into 4 upon 2. Which is 10. So 10 x cube y square. Again 5c3 is equal to 5c2. So it will become 10 x square y cube. This is symmetric. 5c4 is 5. 5x y to the power 4. And this is 1. So the coefficient of x to the power 5 will be equal to coefficient of y to the power 5. The coefficient of x to the power 4 y will be equal to the coefficient of x y to the power 4. So basically the coefficient of x to the power n minus k y to the power k, the coefficient of this will be equal to the coefficient of x to the power k and y to the power n minus k. Right? Either you can select k y's or k x's, it doesn't matter. And both these coefficients will be n c k. Right? So that's how you can do it. And there is an interesting observation. Like so if you see, I will come to the sum. Like there is an interesting observation. So this, if you just put all these coefficients in a fashion, actually you can create a beautiful triangle. So what is x plus y to the power 1? It is just x plus y, right? So here you are having just one coefficient. So what is x plus y whole square? It is x square plus 2xy plus y square. What is x plus y whole cube? It is x cube plus 3x square y plus 3xy square plus y cube. Similarly, what is x plus y to the power 4? It is x to the power 4 plus 4xy cube plus 6x square y square plus 4x to the power 3y plus y to the power 4. So if you see, we are actually creating a beautiful triangle here. And how is it created? If you just write the coefficients this way, 1 for x plus y, actually 1. For x plus y, the coefficients are 1. For x plus y whole square, the coefficients are 1, 2, 1. For x plus y whole cube, so this is binomial theorem for power 1, this is binomial theorem for power 2, binomial theorem for power 3 will be what? The coefficients are 1, 3, 3 and 1. For x plus y to the power 4, the binomial coefficients will be 1, 4, 6, 4 and 1. There is a symmetry, right? For 5, the coefficients are 1, 5, 10, 10, 5, 1 and so on. This is called the Pascal's triangle. And you can have x plus y to the power 0 as well. X plus y to the power 0 is just 1. Right? This is called the Pascal's triangle. Here if you observe a fact, every term is the sum of these two terms. So here this term is sum of these two terms. This 10 is the sum of 4 and 6, or you can do 6 and 4, right? 4 and 6. This 10 is sum of 6 and 4. This theorem also we have seen. This we have seen in combination as recurrence, right? We saw that n choose r is n minus 1 choose r minus 1 plus n minus 1 choose r. Right? This theorem we have seen in combinations as recurrence. So this is what? This is 5c2. 5c2 will be 4c1 plus 4c2. This is 4C1, this is 4C2. Right? So if you see this triangle carefully, this will be 4C0, 4C1, 4C2, 4C3, 4C4. This will be 5C0, 5C1, 5C2, 5C3, 5C4, 5C5. So 5C2 will be 4C1 plus 4C2. Combination as recurrence. Oh, yeah, so like you can just add the above two terms and you'll get the below term. So this is math, like if you are writing a computer program, that's how you generate the Pascal's triangle. Just sum the above two numbers and you'll get the number below. So like everything is connected, right? Like whatever we have seen so far. So everything is connected. Like this theorem is being applicable here, and this is a beautiful triangle called Pascal's triangle. And another property of Pascal's triangle is it is symmetric. Like this we already saw, right? This is symmetric along the horizontal line. It is symmetric because n choose r will be equal to n choose n minus r. That is also one thing. And the next interesting property is what is the sum of all binomial coefficients. So for n equal to 0 the sum is 1. For n equal to 1 the sum is 2. For n equal to 2 the sum is 2 plus 1 plus 1, which is 4. For n equal to 2 the sum is 1 plus 3 plus 3 plus 1. The sum becomes 8. For n equal to 4 the sum is 1 plus 4 plus 6 plus 4 plus 1, which is 16. 32. You see a pattern here. For n equal to n, the sum of all binomial coefficients is always 2 to the power n. For n equal to 0 it is 1, for n equal to 1 equals 2, 4, 8, 16, 32. So for any n, the sum of all binomial coefficients is always 2 to the power n. And we can actually have that interpretation here. How? Why is it always 2 to the power n? So let's see that. Okay. So this is what x plus y to the power n was. N choose 0, x to the power n. N choose 1, n choose 1, x to the power n minus 1, y. N choose 2, x to the power n minus 2, y square. N choose n, x to the power n, x to the power 0, y to the power n. This is binomial theorem. What is the sum of coefficient? Sum of coefficient is n choose 0 plus n choose 1 plus n choose 2 up to n choose n. How do you calculate it? Just put x and y as 1 here. Just put x and y equal to 1 here. If you put x equal to y equal to 1 here, you will get what? This will become 2 to the power n. This will become 2 to the power n, and this will become nc0. These terms will all become 1, 1 to the power 1, 1 to the power n minus 1 into 1. So these will all become 1. So this will become 2 to the power n equal to n choose 0, n choose 1, n choose 2. So the sum of the coefficient you can calculate by putting x and y both as 1, and it will be equal to 2 to the power n. And you can also see it using the motivation that we saw in the last lecture. So in the last lecture we saw, in this lecture only, previously we saw that how is the binomial theorem actually even calculated? How are we actually representing the binomial theorem? So we say that x plus y to the power n is what? You are just multiplying x plus y n times. So you have n brackets, you have n containers. You can take an x or a y from each one of them. You can take an x or a y from each one of them. And what is the sum of all coefficients? See, I told you the coefficient of any term. The coefficient of any term is what? The coefficient of any term is what? Let's say x to the power k, y to the power n minus k. You are picking k x's and n minus k y's. You are actually picking k x's and n minus k y's. So basically, if you want to sum the all coefficients, the coefficient of this term is the number of ways in which I can pick k x's and n minus k y's. So what will be sum of all the coefficients? It is like the number of all possible ways, right? Either you are taking n x's and 0 y's. So you are taking 0 y's or 1 y or 2 y or 3 y. Basically, you are taking, like, the sum of coefficients will be all possible ways in which you can multiply this equation. Or basically you can take an x or y from each of the containers. So what is the number of all possible ways? you have two options for every container. You can take an x or y from here. You can take an x or y from in the second container. And similarly, you can take either an x or a y from this container. You have two options for every container. So the total number of possible ways in which we can do this thing will become 2 to the power n. So combinatorically speaking, also like container wale way se we are getting like the total number of ways will be 2 to the power n. Also from the formula of binomial theorem, we are getting the sum of coefficients as 2 to the power n. So this is the mapping. Like that's why we are discussing it here. This is the mapping of counting with the binomial theorem. Okay. So this was about binomial theorem. A more complicated version of binomial theorem is the multinomial theorem. But I should say that binomial theorem is actually a subset of the multinomial theorem. So we will discuss the multinomial theorem now. So in binomial theorem, there were two unknowns, x and y, x plus y to the power n. Or basically in every container, there were only two objects, x or y. You can pick an x or a y. In multinomial theorem, you have multiple number of objects in every container, that's it. So basically here also you have n containers. Previously in every container, you just had an x or y. But here, you will have m different options in every container. So previously you only had x and y. Let's say now you have x1, you can have x1, x2 up to xm. You have m different options in first container. Similarly, you have m different options in second container. x1, x2 up to xm. Similarly, you have m different options in nth container. That's what multinomial is, right? Like you don't have two options, you actually have m options in every container. So what you are trying to do is you're trying to expand x1 plus x2 plus xm to the power n. In binomial theorem we had x plus y to the power n, only two like variables, right? Here we have m variables. So x1 plus x2 plus x3 up to xm to the power n. So this is like multiplying x1 plus x2 plus xm. This is first bracket, this is second bracket, and this way we are multiplying them n times. So we have n containers, we are multiplying this bracket n times. So here how the coefficients will look like, you can either take an x1 from all the containers, so you will have a term like x1 to the power n, or you can take, let's say, n minus 1 x1s and 1 x2, or you can have n minus 1 x1s and 1 x3. There are many such terms, and like one of the terms will be, last term will be xm to the power n, right? But again, see, how will one term look like? Any one of these terms will look like this. It will be x1 to the power, it will be x1 to the some power, let's say k1, then x2 to the some power, let's say k2, and multiplied like this, xm to the power km. Every such term will look like this, and the sum of all these powers will be what? N. Sum of all these powers will always be n, because you are picking some object from every container. The total number of containers is n. So the total number of objects you will get will always be n. You will have some number of x1s, you will have some number of x2s, some number of xm's. The sum of all these powers, k1 plus k2 up to km, will always be n. Okay, so every such term will look like this. Every term will look like this. Now, only thing we need to do is find the coefficient of this term. Any generic term in multinomial theorem looks like this. You just have to find the coefficient of this term. And if you have seen my last video, we have already solved some like one such problem. So what do we want here? We just want to find the coefficient. We just want to find the coefficient of. So we want to expand this, and we want to find the coefficient of one generic term, any generic term. So let's say that term is x1 to the power k1, x2 to the power k2, xk to the power xm to the power km. We have to find the coefficient of this term. Will be what? Okay. So it is like the number of ways in which we are taking one object from first bucket, one object from second bucket, one object from nth bucket, and all the buckets have m items, right? x1, x2 up to xm, same items. So in such a way that we are taking k1 x1 items, k2 x2 items, k3 x3 and so on km xm items. The sum of k1 k2 up to km will always be n. The sum of k1 k2 will always be n. So in how many ways can I do that? So basically like just do it like Binomial theorem only, okay? So out of the n containers, pick any k1 containers. Out of the n containers, pick any k1 containers and pick an x1 out of them. So this will be much easier if I take an example, okay? Then I will do a generic version. So let me take an example. Let's say we want x1 plus x2 plus x3 to the power 7. And here I want to find, let's say I want to find the coefficient of x1 to the power 3, x2 to the power 2, x3 to the power 2. This is one such valid term in the expansion of this, right? The sum of the power will always be 7, 3 plus 2 plus 2, 7. This is one such term. And let's say in the expansion of this, I want to find the coefficient of this term. So how will I do that? Basically, I have 7 containers. Each one of them have one x1, x2 and x3. In how many ways can I pick 3 x1s, 2 x2s and 2 x3s? How will I do that? Out of the 7 containers, take any 3. I am using the rule of product. This is my first task. Pick 3 x1s. This is my first task. First task, pick any 3 x1s. So out of these 7 containers, pick any 3 containers. I will take x1 from them. Now from the remaining 4 containers, pick any 2 containers and take 2 x2s from those. And now from the remaining 2 containers, take both the containers and pick 2 x3s from there. So this is by rule of product, this is my answer. And the order doesn't matter. You can take first x1, then x2, then x3, or let's take x3. So for x3, let's say from the 7 containers, I am taking any 2 containers. From the 7 containers, I am taking any 2 containers and I am taking the 2 x3s from here. The order doesn't matter, right? And then my second task is, let's say I first pick x3, then I pick 1 and then 2. So now from the remaining 5 containers, pick any 3 and take 3 x1s from there. Then from the remaining 2 containers, take both the containers and take the 2 x2s from there. These two products are same. It doesn't matter. How? If you expand it, it will come out to be 7 factorial upon 3 factorial, 4 factorial. The first term. The second term will be 4 factorial upon 2 factorial, 2 factorial. And the third term will be 2 factorial upon 2 factorial, 0 factorial. Right? So these will cancel. And you will have 7 factorial upon 3 factorial, 2 factorial, 2 factorial. It is just like 7 factorial upon 3 factorial, 2 factorial, 2 factorial. If you expand this also, you will get the same thing. The first term is what? 7 factorial upon 5 factorial, 2 factorial. The second term is what? 5 factorial upon 2 factorial, 3 factorial. Yep. And the third term will be what? 2 factorial upon 2 factorial, 0 factorial. You can cancel this and this, this and this. Here also you will get 7 factorial upon 2 factorial, 3 factorial, 2 factorial. This and this are same. Actually, this is called this is defined to be 7 choose 3 comma 2 comma 2, and this is also defined to be 7 choose 2 comma 3 comma 2. So the order doesn't matter. Okay, basically what you are doing, from 7 objects you are picking 3 objects, and then from the remaining objects you are picking 2 objects, and then from the remaining objects you are picking 2 objects. Here also you are doing 7, from 7 you are picking 2, then 3, then 2. So the order doesn't matter, just the total number of objects you are picking is 7, and you are picking 3 and 2 and 2. Right, 3 x1s, 2 x2s and 2 x3s. So in which order you are picking, it doesn't matter. So firstly you pick 3, then 2 and then 2. So this is what 7 choose 3 comma 2 comma 2 is like. Okay, so this coefficient will be equal to 7 choose 3 comma 2 comma 2, which is 7 factorial upon 3 factorial 2 factorial 2 factorial. Similarly here, this coefficient of x1 to the power k1 will be what? Since the sum is n, it will be n choose from the n containers. Pick any k1 containers and choose x1 from them. Then from the remaining n minus k1 containers, choose any k2 and pick an x2 from them. Then from the remaining n minus k1 minus k2, choose any k3 containers, and so on. This product, if you calculate it, it will always come out to be n factorial upon k1 factorial, k2 factorial, k3 factorial, and so on up to km factorial. And this is called n choose k1, k2, km. Okay, this is the multinomial coefficient of x1 to the power k1, x2 to the power k2, xm to the power km in the expansion of x1 plus x2 up to xm to the power n. It is the number of ways of choosing k1 x1s, k2 x2, km xms in n containers, where every container contains one x1, x2 and xm. Okay, so this expansion you can do like this. Okay, things will cancel out and it will automatically come out to be this always. I can do it for you very simply, like very easily. So let's say like the coefficient was what? N choose k1 times n, from the remaining n minus k1 you choose k2, then from the remaining n minus k1 minus k2 you choose k3, and so on. The last term will be n minus k1 minus k2 up to km minus 1. Okay, so this term, let me finish it. So this choose km, from the remaining terms you choose km, this will be the last term. We know that the sum of k1, k2, km minus 1, km will always be equal to n. So this term will automatically become km at the end, this entire term. At the end you will only be remaining with km items only. From km you will choose km. So what will this product be? N factorial upon k1 factorial, n minus k1 factorial. This term will be what? N minus k1 factorial upon n minus k1 minus k2 factorial, k2 factorial, and so on. At the end you will have km factorial upon km factorial, 0 factorial. Always these terms will cancel. So you will have n factorial upon k1 factorial, k2 factorial up to km factorial. Okay, so this is the coefficient and this is how it is defined. So this is how in compact notation we will write the multinomial theorem. x1 x2 plus xm to the power n is what? Summation of all such terms. Summation of all such terms in which k1 plus k2 plus km should be n. There are many such ways in which we can do this. Summation of all such terms in which k1, k2 up to km is equal to n, and all these k's are greater than or equal to 0. This is my term. This is how my term looks like. x1 to the power k1 times x2 to the power k2, x2 to the power k3 multiplication. This is product. So this is my term. This expansion is what? x1 to the power k1 times x2 to the power k2, and so on, xm to the power km. This is my one such term. Okay, so for all such terms the coefficient is n choose k1 k2 up to km, where n choose k1 k2 up to km is this, n factorial upon k1 factorial, k2 factorial, km factorial. Okay, I hope you got it. So there are a couple of problems on multinomial theorem. So like one is, what is the sum of all multinomial coefficients? Very easily, like binomial, how will you do it? Just write x1, x2, xm all 1. You will find the sum of coefficients. So you will get 1 plus 1 plus 1 to the power n is equal to, so this term will become 1. If you put all x is equal to 1, this term will become 1, right? So you will get the sum of all possible coefficients, like just like binomial. So sum of all possible coefficients is what? This thing. So it is just 1 plus 1 plus 1 m times. So it is m to the power n. So in binomial theorem it was 2 to the power n. In multinomial theorem it is m to the power n. And what is the number of multinomial terms? What is the number of multinomial terms? So in how many ways? So see, right? How many such terms exist? That is the question. So in the expansion of, let's say, x1 plus x2 plus x3 to the power 7. I told you there will be many terms. x1 to the power 7, x1 to the power 6, x2, x1 to the power 6, x3, x1 to the power 3, x2 to the power 2, x3 to the power 2. That is one term. So how many such terms are there? So it is exactly like, see, so the power of x1 is k1, so the power of x2 is k2, and the power of x3 is k3, and all the sum of all the powers have to be 7. So the number of solutions to this equation, where k1, k2, k3 has to be greater than or equal to 0, is the number of terms we will get. It is always equal to the number of terms that we will get. We already know how many solutions are there to this equation. This is 7 plus 2, 9c2, right? So similarly, in a generic expression, what will happen? We have k1 plus k2 plus km is equal to n. How many solutions are there to this equation? It is n plus m minus 1. Choose m minus 1 or m plus n minus 1. Choose n. You can write anyway. Okay. Just the formula that we saw before. So this is the number of terms that we will have. So the sum of multiple coefficients is m choose n, m to the power n, and the number of terms is n plus m minus 1, choose n. Okay, see carefully, okay, don't get confused. It's not here r is n, right? So that's why, like, always convert it to an equation. Generally we have r here. So don't get confused. Convert it into equation and just apply the logic. Like, you want to make m partitions, so you will insert m minus 1 sticks. So that's the formula, okay? Cool. So this problem we already saw in the last lecture. Your mother-in-law has 1,000 small gifts to give to relatives, 1,000 different gifts, and there are 25 relatives in which to which you have to distribute these gifts to. In how many ways can these gifts be distributed so that each person gets 40 items? So again, we have 1,000 gifts, and now it will be more clear to you how to solve the problem. And you have 25 relatives. Each person should get 40 gifts. So it's like you choose any 40 gifts for R1. So it's like from the 1,000 gifts you choose any 40 gifts and give to R1. Every person should get 40 items exactly. And the items are different. So you choose any 40 items, give it to R1. Then from the remaining 960 items you choose 40 items, give it to R2, and so on. From the remaining 40 items you choose 40 items and give it to this relative. And this is nothing but from the 1,000 items we are choosing 40 items, then 40 items, then 40 items, up to like 25 times. This is also the multinomial coefficient of x1 to the power 40, x2 to the power 40, up to x25 to the power 40 in the expansion of x1 plus x2 plus x25 to the power 1,000. Right? So, like, if you want to see the combinatorial interpretation, think it like that. You have 1,000 items, right? For the first item, you can give it to any of the 25 relatives, x1, x2, or x25. The second item you can give to any of the relatives, to 25 relatives. The 1,000th item you can give to any of the 25 relatives. But now we want to find the coefficient of this only. Why? Because x1 should get 40 items. X2 should get 40 items, and the 25th relative should also get 40 items. Okay, so this is how you can do it. So if you want to see the final combinatorial interpretation, this is how you say it. This is like the multinomial theorem is nothing but the ways in which we put objects into bins. So the multinomial coefficient have a direct combinatorial interpretation as the number of ways of depositing n distinct objects into m distinct bins with k1 objects in the first bin, then k2 objects in the second bin, and so on. Okay. So we will see more problems on binomial and multinomial theorem. This was the theory part. This might be a little tricky, so just watch the video again. If you have any doubts, write in the comment section. I will answer them. And also, when we solve more practice problems, these theorems will become more clear. Okay. But yeah, like seeing the combinatorial interpretation of every theorem and then like writing the equation and solving it will help you. Don't jump directly to formulas. Try to see the mathematical way. Why is this problem being solved that way? Okay. Cool. See you tomorrow, and we will discuss the principle of inclusion and exclusion. Bye bye.